This experiment is about determination of delta octahedral for several complexes by changing the ligands and building a spectrochemical series. The first is a reminder of the cobalt uh, complex, which forms a low spin D6, the cobalt 3 plus, and this is the ligand field. 6 ligands with 12 electrons interact with D, S, and P of the cobalt. Now you have 6 bonding orbitals at the bottom, lower energy, and you have the T2G orbitals, 3 orbitals, and the EG, as you know, and delta octahedral is the separation between the T2G and the EG. You have the 6 cobalt electrons in the lower T2G, and it's the ground state is an A1. Now you start with the cobalt NH35Cl, and you start changing the ligand Cl to H2O to ammonia to NO2, and you record the lambda max, which is the only absorbance because it's A1 to T1, one absorbance, and it represents the delta octahedral. This slide shows the variation in sigma donation, pi donation, and sigma donor pi acceptor ligands. In the middle, you find the sigma donor ammonia with delta octahedral between T2G and EG. And when you have a pi donor ligand like Cl minus, it shifts the T2G towards the EG star, and the delta becomes smaller. When you have a sigma donor pi acceptor ligand on the left, you lower the energy of the T2G, and the EG star stays the same. So the separation between T2G and EG star becomes larger, and delta becomes the largest of all. So the sigma donor pi acceptor is the largest, and the sigma donor in the middle is smaller than sigma donor pi acceptor, and the pi donor is the smallest, resulting from the pi donation shifting the T2G to higher energy. Now the cobalt complexes we are going to prepare. One contains the hexaamine complex, which has a low spin, large delta value because of the energy match between the ammonia and the cobalt, and the ammonia is sigma donor, so low spin D6, and the color is yellow-orange color, and the absorbance is low for 30 nanometer. Now when you change one of the ammonias to H2O, the color starts changing to red, which means delta is getting smaller, and the absorbance in lambda gets higher, 493, shifts from 430 to 493. Then when you change to pi donor ligand Cl minus, it goes to complete red, our reddish complex, and the absorbance at 528. When you put NO2, for example, it shifts to the other direction and becomes yellower complex, and it absorbs at 450 something. This is the color changing in the complexes we're going to prepare. So you build the spectrochemical series according to the delta value or lambda value. Now all you have to do to convert the lambda in nanometer centimeter minus 1, and you report delta values in centimeter minus 1. Now the orbital splitting, as we saw in the previous slides in octahedral complexes, gives A1 in the ground state, when you have T2G6 and EG0, and when you excite the electrons, you have only one spin allowed state, which is T1. So you have one absorbance, A1 to T1. Now the types of ligands we're going to use sigma donor ligands like the ethylene diamine NH3. So in this experiment we use the NH3, which is in the middle here, sigma donor. Then we change to Cl minus H2O pi donor ligands, weaker. Then to stronger ligands like the NO2 minus sigma donor pi acceptor ligands. The ligand's strength is parallel to the basicity, because ligands here are Lewis bases and the metal is a Lewis acid, and the complex bond is an adduct bond. So you have, for example, the high effective nuclear charge for F minus makes delta larger than the low effective nuclear charge for I minus. So the arrangement is F minus stronger than Cl minus, stronger than Br minus, stronger than the large atom I minus, and H2O being a pi donor is stronger than F minus. The whole arrangement at the bottom of the slide is the sigma donor pi acceptor ligands are the strongest, CO and Cn minus. We can add to them NO2 minus and phenanthroline. Then comes the sigma donor ligands, ammonia and ethylene diamine, NCS. Then the pi donor ligands, H2O, F minus, acetate, OH minus, Cl minus, and you arrange your complexes according to the absorbance of the complex in the UV visible. Now, we cannot ignore the effect of metal ion size and charge on the delta octahedral, but here we have the complex only for one metal ion with the same charge, so the effect of metal ion charge is eliminated, but we have to keep in mind that metal 3 plus delta is always larger than metal 2 plus delta in all complexes. For example, delta for cobalt 3 plus is larger than delta for cobalt 2 plus. Fe3 plus delta is larger than Fe2 plus. And the absorbance band here originates from A1 in the ground state to T1 in the excited state. Now the Cl minus the Cl minus ligand, as we said, is a pi donor ligand and makes delta smaller, and the same arrangement here at the bottom of the slide, I minus, Br minus, Cl minus, F minus, and NH3. Now the difference in absorbance between the hexaamine complex, which is uniform, the excited state is T1 split into T1 1 and T2 1, and if you replace one of the ammonias with Cl, there is a splitting in the state to E and A, so you see the little shoulder at the bottom of the screen. Is different because the field is not uniform as in the hexaamine complex. Now we turn to the preparation of the complexes. The first complex, the pentaamine NH3 5 chloro complex 1Cl, you prepared in experiment number 1 and you kept it in your locker. Now if you didn't save the complex, you can always prepare it in an easy couple of steps I will show you later. If you have the complex cobalt NH35Cl, all you have to do to prepare the aqueous complex, you replace the Cl minus with H2O by dissolving the complex and adding aqueous ammonia and at the end you add HCl. You stir for a while and you end up with a reddish complex, which is the H2O complex number 2. Now, this is the preparation of the chloro complex. If you don't have it, or you don't have enough of it, you can prepare it by adding 1.7 gram ammonium chloride, NH4Cl, cobalt, then in 10 mil concentrated ammonia, NH3, in a 400 ml beaker. Then you stir continuously, and 3.3 gram cobalt 2 chloride added to the mixture, and you stir. You add 2.7 mil 30% hydrogen peroxide to oxidize the cobalt 2 to cobalt 3, but you make sure to add the hydrogen peroxide drop wise to avoid splashing of the mixture. Then you stop the reaction. 10 ml concentrated hydrochloric acid, you add them slowly to the mixture. You continue stirring, and you heat the mixture to 85 degrees centigrade for 20 minutes, and cool the mixture. You get the chloro complex you need for preparation of other complexes, and you need it to record the lambda max for this complex as well. Now, the other complexes, which is the NO2 minus, but bound through the oxygen. It's called the nitrito complex. You prepare it from the chloro complex by adding the nitrite. You make sure that you have nitrite, NO2, sodium nitrite, and you add HCl. You stir, and the procedure, you prepare the ONO, which is reddish in color. You have to make sure, and you keep a little bit for the absorbance, and then you convert this ONO complex number 3 to NO2 complex isomerization. You change the bonding from O to nitrogen down there, so the delta value becomes larger, and you have stronger binding through NO2. And at the last complex, the hexamine complex, you can prepare it in this procedure: 50 ml beaker, 0.8 gram cobalt chloride hexahydrate, 1 gram ammonium chloride, then 0.08 gram activated charcoal. Add to 50 ml beaker and 4 ml water. Dissolve the complexes. Always make sure that the complex, especially in this step and the other step, when you convert the ONO to NO2, make sure that the ONO complex is completely dissolved and the solution is clear. Otherwise, it doesn't react. In this reaction, you prepare the hexamine complex. You stir 1.75 ml 30% H2O2 or hydrogen peroxide, then heat 60 degrees for 30 minutes. You get your complex. It's a yellow color complex. Then you record the absorbance of all your complexes by preparing low concentration. You calculate the molecular weights, and you prepare in a volumetric flask, low concentration, 10 to minus 2 molar, and you record the UV visible spectra of all these complexes, and you arrange them according to ligand strength. You answer the questions, the percentage yield in the report of all your complexes, the UV visible spectra from 650 to 400, and you tabulate the results of delta in centimeter minus 1. I don't want you to calculate in joule or anything, just tabulate the results in centimeter minus 1. Verify the position of the ligand strength. Explain why, as I explained in this lecture, how the delta changes from Cl minus to NH3 to the reason for changing delta in each of these complexes. And this will conclude the experiment about the spectrochemical series.